All right, so like I said, we're starting chapter 11 today. Chapter 11 is all about oxidizers and oxidizing agents. So we're moving away from kind of the stuff that can kill you by messing with your body mechanics and getting back to things that are more chemically reactive with a broader range of substances. So we need to kind of start with a overall definition of oxidizers, of oxidizing agents, so that we can learn to recognize when an oxidation reaction is occurring and kind of, what we can do about it. So what we have to understand is that oxidizing reactions, redox reactions in general, do have important uses for us. If we are able to control the chemical reaction, control the rate of oxidation, the energy that comes from these kinds of reactions can actually be very useful. We can capture that energy, we can harness that energy, and put it to use. Great examples of this are things that like electrochemical cells, batteries, dry cells, fuel cells, where in the chemical reaction that is taking place, the energy that is being produced through that reaction is enough to provide us with electrical current. And that electrical current is the kind of stuff that we do often. Most of what we're trying to do is in that kind of realm. Cell phones, computers, tablets, most of the technology that we own and operate. And even if we look at like things like electricity, which isn't a battery kind of reaction, but it is still an electrochemical. What happens in that is, here in Indiana, we burn coal. Coal runs the thermal energy plant, which produces enough heat to turn water into steam. The steam turns the turbine, which turns the generator, creates all of our electricity. That combustion reaction is a redox reaction. It's a controlled one. So even though we don't think about combustion reaction as being electrochemical, the reaction itself is a redox reaction. And the reaction itself does end up yielding electricity for us in an indirect way because of what we do with that energy that we harness. But redox reactions can also get out of control. And if we have an uncontrolled redox reaction, that redox reaction can take the energy that is produced and release it into the immediate environment around it. And the net result of this energy, of this supplement of oxygen, is that the energy can help to initiate a fire. We can end up intensifying a fire. Or we can have enough energy present with the kind of right combination of factors to actually cause an explosion. So what is it that we have to look out for? What is an oxidizer? Well, oxidizers, which also can be known as oxidants or oxidizing agents, are substances that on their own will support combustion processes. So these are substances, generally speaking, that aren't flammable themselves, but do have the capability of feeding a fire and supporting a fire. Now, in most cases, we think of oxidizers, at least in the support of combustion, as being some kind of substance that will either generate oxygen through its decomposition or in some way involve oxygen in its process. And that's what leads to the fire itself kind of being fueled. But there are other oxidation processes that can occur where we have stuff that is free of oxygen. So some common oxidizers in general are things like oxygen, just plain old oxygen gas, fluorine gas, chlorine gas. These are all good. As acting as oxidizing agents. And if you want to know something that's really interesting, chlorine and fluorine are actually way better at oxidizing than oxygen. Comes down to the idea of going back to where we were in chapter 4, looking at where fluorine and fluorine are in terms of how close are they to getting their octets. Well, because of that being only one electron away, fluorine and fluorine are very hungry for electrons. So as a result, they're a lot more reactive. Now, fluorine and fluorine aren't going to have the same kinds of effects on combustion reactions as they do on other kinds of reactions, but they are better oxidizers just in general. Now, when it comes to classification, there are two subclasses of oxidizers according to the Department of Transportation. The two subclasses are the inorganic oxidizers. These are the ones that are metallic-based or metallic compounds that include in some kind of an oxidizing agent. We generally refer to these broadly as oxidizers. And then there are the organic peroxides. And what makes them special is that when these organic peroxides undergo their reactions, they end up producing a flammable substance in addition to oxygen. So the decomposition of an organic peroxide basically creates its own fire. Because what you end up with is a flammable substance like an alcohol or some other kind of organic, and you end up having oxygen as well. Now, by definition, DOT, Department of Transportation, defines an oxidizer as a substance that may enhance or support the combustion of other materials, usually by yielding the oxygen inside of it. And so, under this DOT definition of oxidizers, what you are going to find is that most of them are going to be oxygenated compounds of some kind. Because in order to give up an oxygen, you have to have oxygen in your chemical formula somewhere. Now, OSHA and the Global Harmonized System have slightly different definitions for oxidizers. OSHA looks mainly at the phase, and so anything that can be considered an oxidizing gas, an oxidizing liquid, or an oxidizing solid all get lumped up into the group of oxidizers according to OSHA. If we're looking at liquids and gases, the sidecar kind of here is that those substances can cause flammability characteristics. So we have a material that's flammable or combustible that's present with this oxidizer, and it's able to cause that oxidizer to decompose, give up its oxygen, and cause the material that is burning to continue to burn or to accelerate in its burn. So those are our regulatory definitions of oxidizers. Unfortunately, that doesn't really give us a whole lot of information in terms of, okay, how do I identify a substance other than I pick up a bottle of it and I see the placard there. If I'm looking at a chemical reaction, if I'm looking at a, kind of theoretical chemical equation, how do I go about looking for and deciding if an oxidizer is present if I'm looking at a redox reaction? And the best way to kind of go about it is the recognition that there are always going to be two processes in play when we see these oxidation reactions. These reactions are referred to as oxidation reduction or redox because two processes are taking place at the same time. The first of which is oxidation. Now, oxidation can come up in a variety of forms. We can see things in terms of what we call the oxidation number. Oxidation number we can think of as the individual charge on an atom in a molecule. We're not going to spend a whole lot of time talking about oxidation numbers, but we might mention a couple of them in passing. What's important when we think about oxidation numbers, though, is that generally speaking, the more extreme the oxidation number is, the more reactive we tend to see it become, especially on the positive end of the scale. If we see oxidation numbers around +7, +6, +5, what that tells us is that that particular atom is especially electron deficient. It's lacking electrons. And since it is lacking electrons, it is going to be very susceptible to being an oxidizer so that it can gain some of those electrons back and get a little bit more stable. And so when we get into some of the examples next week, we'll feature some of those kinds of compounds and we'll point them out specifically. Hey, this has a +6 oxidation state. It's pretty reactive. What we can look on more often, though, is we can look for things like a loss of electrons from an ion. So something goes from being a negative ion to a positive ion, or a negative ion to a neutral atom, or even from a positive ion to a more positive ion. The act of losing electrons is a way to identify oxidation. Another way is looking for the movement of oxygen. If we see that oxygen atoms are being given to an atom or to a molecule, we can generally talk about that molecule being oxidized. If you want to talk about the literal definition of oxidation, it is the addition of oxygen to a substance. So if you think about a combustion reaction, in a combustion reaction, we have carbon reacting with oxygen. We can clearly see that as that carbon turns into carbon dioxide, it has been oxidized in the process. Reduction is the other way. With reduction, we are looking mainly at decreases in oxidation state. So getting more negative instead of more positive. So if we notice that an atom goes from having no charge to a negative charge, if we notice that an ion, a metal ion, goes from a more positive state to a less positive state, or a more positive state to a zero state, that's a reduction. That is gaining electrons and decreasing the overall positive charge. And so this idea of gaining electrons is an idea that we can kind of get behind when it comes to reduction. So there's an easy way to keep this kind of straight. The simple mnemonic device. Oil rig. Oil rig stands for oxidation is the loss of electrons, OIL. Oxidation is loss. Rig, reduction is gain. So if we're looking at things from an electronic standpoint, oil rig can kind of help us to figure out what's being oxidized, what's being reduced by tracking the electrons. Now, it's not always easy to track the electrons. Sometimes instead, we end up tracking oxygens instead. So in oxidation, we look for increases in atoms of oxygen. In reduction, we look for decrease in oxygens instead. Oxidation is loss of electrons. Reduction is gain of electrons. Now, one other thing that's important to know about redox reactions is that sometimes redox reactions are presented in kind of a stripped down form. Where, if you remember when we talked about replacement reactions, we talked about the idea that sometimes you had the same ion on each side, nitrate ion on one side and nitrate ion on the other side, sulfate ion on the one side, sulfate on the other. And we used it in balancing to kind of cluster them together, make the balancing a little bit easier. Well, in redox reactions, sometimes what we'll notice is that some of the ions that are involved don't actually participate in the reaction itself. Those are called spectator ions. And when there are spectator ions, it is not an uncommon occurrence to see those electrons just removed from the chemical equation. And so from that standpoint, the reactions can kind of look a little bit incomplete when those spectators are removed. Where maybe instead of aluminum hydroxide or aluminum nitrate, we just see the aluminum ion, Al3+. Because in the end, the nitrate ion didn't do anything. Hydroxide ion didn't participate in the reaction at all. So we just kind of take it out and work with what actually did change. And a lot of times that's useful because it helps us to point out a little bit more clearly what actually changed and what actually stayed the same. Now, there are two other terms that we have to familiarize ourselves with redox reactions. They are the oxidizing agent and the reducing agent. Now, here's where it can get a little bit confusing. Both of these substances will come from the reactant side of the equation. The oxidizing agent and the reducing agent will always be reactants. There are two important pieces of information that we have to gather from it. First of all, the oxidizing agent is going to include the substance that ultimately accepts electrons. Now, you may be sitting there going, well, wait a second. You just told me oil rig. Reduction is gain of electrons. Accepting electrons would be gaining electrons. Why on earth are we calling that the oxidizing agent when it's a reduction that's taking place? Good question. Unfortunately, what we have to think about here is that when we're talking about these agents, we're talking about what they force the other substance to do. So an oxidizing agent forces the oxidation of another substance. Forces that substance to give up its electrons. And in the process of forcing that other substance to give up its electrons, it takes them in. And that addition of electrons is going to help one of the elements that is in that reactant. And a reducing agent is exactly the opposite. A reducing agent is going to contain a substance that is going to give up its electrons. So another way of thinking about that is the reducing agent is basically taking its electrons and shoving them into the pocket of the thing being reduced. Please take this, I don't want it. The important thing to remember is that there is a difference between oxidation and reduction and oxidizing agents and reducing agents. Oxidation and reduction occurs at the elemental level. An individual element gets oxidized or gets reduced. Manganese gets oxidized. Manganese gets reduced. Oxygen gets reduced. Fluorine gets reduced. Whatever it is. Carbon gets oxidized. Hydrogen gets oxidized. Individual elements get oxidized, get reduced. It is the substances, in particular the reactants, that contain those those elements that are the oxidizing agents and the reducing agents. Let's take a look at an example here. We need to determine the oxidizing agent or the oxidizer and the reducing agent or the reducer for this reaction. Now, using our definition, not exactly easy to see where the reactions are taking place in terms of the electrons. So this is a good place where we can use that alternative definition about tracking the oxygen to figure out what has been oxidized and what has been reduced. So if I'm looking at these two reactants, which one of them is losing oxygen? Okay, you're right. KClO4 is losing oxygen. So based on that definition, something in here is being reduced. We don't know what, but we know that something in here is being reduced. And what substance is gaining those oxygens? The aluminum. So we know that in this case, aluminum is the only element in this reactant. We know that the aluminum is the one being oxidized. So going back to our definitions, the oxidizing agent is the one that accepts electrons, the one that is being reduced. Our oxidizing agent would be KClO4. That would be our oxidizer. Our reducing agent would be aluminum. Now, if we had access to the oxidation numbers, we could track this that way as well. And just as a point of clarity, I'll do that for you right here. So aluminum has no charge, so its oxidation number is 0. The oxidation number for the potassium is +1. The oxidation number for the chlorine here is +7. The oxidation on each of the oxygens is -2. It's really, for our purposes, it's not important to get into the process. There is a way to do it. It's not terribly difficult algebraically, but I'm not going to get into that detail with you because you really don't need it. Like I said, we can usually track oxygen to figure out oxidizer and reducer. But what we can prove for ourselves here is that we can see that the aluminum has gone to a more positive state. To go to a more positive state, you have to lose electrons. So that's how we can prove to ourselves that the aluminum was oxidized. Like I said, we already rationalized that based on the fact that the aluminum gained oxygen, but we can see electronically how that's possible as well. And for the chlorine, you can see that the chlorine went from a +7 state to a -1 state. It has actually gained 8 electrons in total to do that. The chlorine is actually the thing that is reduced. What you'll notice is that all the other oxidation states here didn't actually change at all. And that is usually the case. Usually when it is looking at it from an electronic standpoint, what we'll find is one element changes, positively, one element changes negatively, and everything else stays the same. But again, for our purposes, this kind of stuff isn't as important. We can usually identify oxidation and reduction by tracking oxygen. And if we can't, then the kinds of examples that we would do would follow the pathway of what the periodic table tells us. So that's how I ended up, honestly. Positive potassium comes from the periodic table. You look at, remember the column definitions that we made for charge back in chapter 4. Group 1, those atoms make positive 1 ions. And oxygen, group 16, those atoms make negative 2 ions. That's where that on the aluminum stays. Group 13, ions of positive 3. The only one that really was different, and that was because that chlorine was attached to other atoms. So chlorine is part of a larger ion called the perchlorate ion, and the perchlorate ion has all of these oxygens on it with that chlorine. That's why it takes on that state. But you can also see, remember I talked about highly positive oxidation states. Here you have a positive 7. Perchlorate ion is a very powerful oxidizer. And you can see why. If I have a positive 7 state, I'm missing every electron in that valence level. I want to get some of them back. In the case of chlorine, got all 8. Went from empty valence shell to full octet. That's how badly it wanted electrons. All right, so what else can we say about oxidizers? Well, we know that they are reactive substances, and their reaction can be quite powerful because they tend to react quite rapidly. Depending on the circumstances, we can even see them reacting explosively with other substances. And these oxidizers can react with pretty much anything that will burn. So you can go anywhere from, kind of your class B, class A, class K substances, fuels, lubricants, greases, oils, plant and animal matter, kitchen fats, paper, straw, charcoal, sawdust, wood shavings, you name it. If it burns, and if it's in the right state of matter, meaning it's got a high surface area or it's volatile in some kind of way, oxidizers can do a lot with that. But what we have to remind ourselves of is that there is a grading system here. Not every oxidizer is going to behave exactly the same way. There are strengths of oxidizers to consider. Some are going to be stronger than others. And it is ultimately the strength of that oxidizer that's going to give us a really good idea in terms of what its reactivity is and what its specific dangers are. So if we go back to that NFPA 704 plaque, remember there's a grading system in that 0 to 4. 0 meant that, and again, we're talking about the yellow diamond in that placard. Classification system for 0 meant that it was completely stable. We had no hazard whatsoever associated with it. The rankings after that were a little bit different. So under class 1, we kind of considered these to be the most stable of the group, or not the most stable, but the least dangerous. These are relatively weak oxidizers. They're not going to do anything to really increase the burning rate, but they will be useful in kind of sustaining the current burning rate. Class 2 oxidizers, now we're talking about something that is going to increase and accelerate the rate of combustion. So that's all that we're talking about with class 1 and class 2. Class 0, completely stable. Does not feed the fire, does not sustain the fire, really does nothing. Class 1 sustains the fire, keeps it burning at its current rate. Class 2 increases the burning rate. Class 3 causes a severe jump in burning rate. So not merely just increasing it, but accelerating it rapidly. And class 4 is increasing the burning rate to such a point that it becomes explosive, or at least it has explosive potential. So those are the differences in the classes. Again, when we talked about these initially in chapter 1, we kind of said, okay, well, what are really the differences? What does a slight increase mean versus a moderate increase versus an explosive increase? So it's kind of relative at that point. But now we have some slightly better definitions to work on. Again, class 0 does not influence at all, does not cause a combustion to accelerate or even continue. It's pretty much inert. Class 1 sustains the fire but does not increase it. Class 2 increases the rate of fire. Class 3 massively accelerates it. Class 4 massively accelerates the fire, has potential for explosion if contamination is introduced or if physical or thermal shock is introduced. So where we go from here is we get into we finish the definition portion of the chapter. Now, all that we are going to do for the remaining 2 days is look at different oxidizers and what makes them different from each other. And so we're going to start with kind of the most common of them, and that is hydrogen peroxide. And when we talk about its common nature, what we're really talking about, this is the one that we're most familiar with. This is the one that we can see on the shelf at Walmart or at a barbershop, a hair salon. What are the differences? What does it actually do? So hydrogen peroxide, chemical formula H2O2. It primarily exists to us in the aqueous phase, meaning the hydrogen peroxide is dissolved in water. Now, as an aqueous solution, it can be in a variety of forms. The one that we're most familiar with is in this first range, somewhere between 1% and 3%. That's what you get on the shelf at the Walmart, at the CVS, at the, you name it. This is primary use for this as a topical antiseptic. You get a scrape on your arm, skin your knee when you're a kid, you go to your mother, she pours the peroxide on there to clean out the wound. It hurts like crazy. You cry about it. That's life. So primary use at that level is basically for cleaning cuts. Put it in there so that, if you got a cut on your arm, if you got a scrape, it doesn't get infected. It's powerful enough to kill any bacteria. You cover it with a bandage, you're good to go. At the 3% level, we see that used more in hospitals. We can also see it added to water as an herbicide to kill off small plant matter, algae, other kind of things like that. At the hair salon, you've ever had your hair commercially bleached for whatever reason, that's about a 6% solution if they use hydrogen peroxide. Chances are pretty good they did not use chlorine bleach because that would hurt like crazy. But 6% hydrogen peroxide is usually enough to do hair bleaching. At these higher levels, we start to get into more industrial kinds of applications, using it to synthesize organic compounds, used in chemical plants, or even in 90% use very specifically as an aerospace solution. Basically, it's a means for generating propulsion in space. A couple of things that are difficult with dealing with hydrogen peroxide. First of all, it is reactive. It's also sensitive. It's light sensitive, which is why if you buy it, you usually find it in either in an opaque plastic jar or something dark. Usually you find it at the drugstore, it's in a brown bottle. That's to block out UV light because UV light will actually cause it to decompose. At higher concentrations, you may not necessarily find it in opaque or brown bottles. You might find it in thick-walled white plastic for the same reason. Usually you have to store it under refrigeration to help prevent its decomposition. Because at higher levels, the decomposition of hydrogen peroxide can cause spontaneous ignition, because what happens is that as it decomposes, it generates oxygen, which is why Hydrogen peroxide has a shelf life. You ever notice there's an expiration date on the bottle? This is why. And if you've ever opened up a bottle of hydrogen peroxide and it made a hissing sound when you did, you know why? The hissing sound is the oxygen getting out. It also means that it's not as concentrated as it could be. It may not do as good of a job at doing whatever it is that you need to do. When you have solutions that are at greater than 20% concentration, those solutions also become corrosive agents as well and can cause very severe irritation, especially to your eyes. And irritating to your eyes to the point of blindness. So that is where we're going to stop for this week. When we come back on Monday, we will continue talking about hydrogen peroxide. We'll actually explore this really interesting case of a Russian submarine from 20 years ago. And we'll get into some other examples of other common oxidizing agents as well. Have a great weekend.